So let's move towards actual climate models. We discussed a lot about simple atmospheric model, radiation budget, and made some very interesting and important points about impact of greenhouse gases on energy balance and feedbacks like temperature, water vapor, CO2, and ice albedo and cloud feedbacks. Let's look at some real models. So here is annual average surface temperature response from an earlier version of the GFDL climate model comparing equilibrium response to time-dependent response. So here is the equilibrium response with significant polar warming in both high latitudes and significant warming in the tropics as well. You have to always remember that the background temperatures here are much colder than in the tropics, so how much the warming is and what it means in terms of the impacts on health, food production, what else? Heat waves, especially because in the tropics, if humidity goes up at some point, the wet bulb temperature is what determines the upper limit of human tolerance for warming, because at 35 degrees centigrade, you can already reach the humidity levels that are so high that the human body will be unable to get rid of the heat with perspiration because the background humidity is already too high, and so on. So those details matter as well. And this is the time-dependent temperature response during years 60 to 80 of the integration, where there is a 1% increase in CO2 per year, and it reaches double the concentration from where you started in about 70 years when you do a 1% increase. Okay, so this is the ratio of time-dependent response to equilibrium response. So you can see that the equilibrium response is much higher in the high latitudes compared to the transient response. And in the tropics they are almost the same. So you can see that this is already almost 3 degrees in the equilibrium response and almost the same in the transient response as well. So energetically speaking, you cannot warm the some regions more than they already warm in the transient response at doubling, because convection begins to move the energy from the heating into the atmosphere and then transport it to higher latitudes, which is part of the circulation changes associated with the equilibrium response. So in that sense, we can come back to climate sensitivity in transient climate change, where surface temperature is still changing. So you have some constant, let's say, heat capacity times delta Ts del T, plus the term we had before in terms of climate feedback term alpha times delta Ts. So again, 1 over alpha is the climate sensitivity, and that is related to the net radiative forcing generated by, let's say, anthropogenic activities, or in this case increased CO2 to doubling. So delta Ts can be written as some gain factor times a transient with respect to the time scale of equilibration divided by alpha, which is the feedback. So 1 over alpha is the climate sensitivity. So the greenhouse, the radiative forcing is here G times T, so increases over time based on the gain, including all the feedbacks in the system that we talked about before. So the net forcing depends on that as we integrate by doubling CO2 at 1% per year. So delta Ts then is G divided by alpha, as we saw before. We had written G equal to alpha delta Ts, and the ocean responds with a lag, which is given by C over alpha. Okay, so that's the coupled system. Atmosphere responds much more faster than the ocean, so the coupled system then is dragged by the ocean in terms of its ability to hold the energy, because right now about 93% of the additional energy from the radiative forcing due to fossil fuel emissions is going into the ocean. So on decadal, multi-decadal time scale, slowly that begins to impact the evolution or the trajectory of the coupled climate. So here is the schematic of transient response to the forcing shown in the upper panel. So we are increasing here, let's say from 1970 to 2100, the radiative forcing in terms of watts per meter squared. You can think of as the radiative imbalance in terms of the incoming short wave and outgoing long wave in the transient, and we are looking at the temperature change associated with that. In the lower panel, the upper solid curve the upper solid curve here gives global average surface temperature response for a climate feedback parameter typical of the more sensitive climate models. Remember that the climate models have a range of climate sensitivities, so some have stronger feedback than the others, while the lower curve would be typical of the less sensitive models. So you can think of that as a range of climate sensitivities in the models. The dashed line shows the temperature for each case that would occur if the ocean did not act to delay the warming. So if the ocean wasn't dragging it down, then the same would be so this one would be here and this one would be here. So that's the range with no ocean delay. Because the response time is longer in the high sensitivity case, which means 1 over lambda is smaller, so the curves initially look similar here, even though the long-term response is very different. Wiggly lines indicate natural climate variability that would occur about the simplified response curve, which we can look at in reference 8. Okay, so the long-term average is the climate and the trend versus the internal variability or the natural variability of the models. Okay, so that's kind of one of the things we do with climate models for projections, to understand how they respond to anthropogenic forcing and which models have high sensitivity and which models have low sensitivity, so high feedback and low feedback, and how the ocean affects the evolution in both the models. They don't necessarily have to be parallel because of the feedbacks and the differences in meridional overturning and so on, and these often do not include, this older version for example did not include land ice models and dynamic vegetation models and so on. So it is still not the final world, which we have to always remember, because climate sensitivity remains one of the biggest challenges to estimate. But the models have been used and are very useful for the so-called attribution experiments, where you take the observed warming of the global mean with respect to some base period like the 20th century or 1961 to 1990, and you give the models all the forcing like anthropogenic fossil fuel emissions, aerosols, land use changes, volcanic forcing, solar activity and so on, and make sure that the models are able to reproduce the observed warming. So this is the range of model simulations of the 20th century, and then in different regions you can see that models are basically doing a good job with better confidence in some regions than in others. So global mean is better than over North America, where the internal variability can be high. Asia is better than here. Europe is similar to North America, and global ocean is better than global land because of the low heat the high heat capacity, and so on and so forth. So there are many reasons why different regions have larger range of model simulations for the 20th century than in other regions, and why land would be different than the ocean, and of course land warming would be faster than the ocean warming because of the heat capacity differences as well. Keeping all that in mind, what you can do is the so-called attribution experiment, where you can use the same models, then take off the anthropogenic forcing and only keep the natural forcings in terms of aerosols and volcanic forcing and solar physics, and see where the warming would be without the anthropogenic forcing. And in each case Systematically, you can see that the forcing without anthropogenic contribution would be much smaller. Only the natural variability would dominate. Of course, there also the range is large, and the differences between the observed warming and natural counterfactual world are also of different magnitude, and also different on land versus the ocean and so on. So this is the best use of models as well, and this is also used for individual weather events, extreme events, cyclones that rapidly intensified, or hurricanes and so on, where it's called attribution of climate event, to see if something like Typhoon Haiyan over the Philippines, or Hurricane Harvey over Texas were made much stronger because of global warming contributions. Do they help with anything? Well, they help to understand the science, of course, and to emphasize the point that global warming and fossil fuel emissions are making contributions at all sorts of time scales in all sorts of extreme events, and so on. Okay, so so this is just showing assumptions. So spatial patterns of estimates of radiative forcing due to effects of human activity, well mixed greenhouse gases from the pre-industrial to the present with 0.2 watts per meter squared in contour, and direct effects of sulfate aerosols. So you can imagine that the industrialized world had the largest sulfate aerosols over time because of the industrial activities, burning of coal and other things. So they typically have a cooling effect. So you can see negative forcing. They are scattering aerosols that are produced by sulfate emissions. So there are also some signals over Africa and of course China. But the well-mixed greenhouse gases have uniformly increased the radiative forcing of the climate over time, and the forcing is high in the low latitudes compared to high latitudes, and this has got many consequences. For example, the impacts like the extended drought over Sahel, for example, could be created by warming due to anthropogenic emissions, which are mostly coming from Europe and US and some countries here till about the 1980s and 90s. After 1990, of course, China is taken off and India is increasing in emissions as well. So all those sorts of things can be seen here. And that comes out also when you do attribution. For example, if you take Sahel droughts that lasted from about 1940s to 1980s, I think, attribution would show that ocean warming drove those things, and not the old story about degrading of land and overgrazing and so on and so forth. And the warming of the ocean could be attributed to emissions which were mostly due to industrialized world. So that's something we have to keep in mind. So we'll come back and look at the kind of scenarios that are created to do these projections into the future. So we have to have a good handle on how the models do in the historic period, how reliable they are, what their biases are, what their drifts are, and so on, and then add the scenarios to them to make future projections. Okay, so we'll look at that in the next podcast.